In this video, we are looking at a new reading skill. And before we get to that, it will be lesson 12. I want to look at the vocabulary for this chapter. You should already have this flashcard made. And let's just review what it's going to be. It's right here. Scientific text. Scientific text is informational text about science that contains academic science vocabulary. This type of text can be very hard to read. It has a lot of, quote, big words that can be difficult. But let's see if we can tackle this and learn some skills that will help us with this type of text. So this is chapter 12 of your reading book, and it's called Understand Scientific Texts. And we are looking at get on the right page 34 in your reading book. So let me get my pencil going here and I'll write that down. Page 34 in the reading book. I want to start with this example. There's really no question to answer here, but we can practice with our mind mapping on this one. Just a couple of things about scientific text. They're going to be nonfiction. They're going to be passages that are about something that is real. It's not a story. It's about something that actually exists. They will contain academic words, and I'll point some of those out to you as we go through here. I'm sure you will be able to spot them. A scientific word is something that you won't see every day. I do recommend using your context clues, but if you don't have those, look it up in a dictionary. Just keep yourself a running list, even in this vocabulary section of your notebook. Any word that you find that you don't know, you've never seen before, go ahead and look that up and get a good definition for the word so that if you see it again, you will know it. Okay, here's our first example. In 2015, the photo of a dress on social media led to a science lesson. Some people saw a blue dress with black lace. Others saw a white dress with gold lace. Why? The answer seems to be due to chromatic bias. Our brains determine which color of light is bouncing off an object. Then they subtract that color to determine the real color of the object. Which color dress we see depends on which color of light our brains determine is bouncing off the dress. So if I were to ask you to pick two words in this passage that you've never seen before, never heard before, I bet just about everybody would name chromatic as one of them. Chromatic is a very unusual word for everyday reading. And also bias. That would be another word that we don't see very often. We're familiar with words like dress, blue, black, brains, color, bouncing. Those are all words that we use on a fairly regular basis. But chromatic bias, that is a tough phrase. So let me just break that down for you. The first thing I want you to know is that anytime you see chroma, think of color. So if you see that prefix or even root, it can be chroma, you are looking at color. So chroma means color, therefore chromatic has something to do with color. And bias, you may have heard this one. Bias is leaning toward one side more than another. So instead of side, if we substitute the word color, chromatic bias is leaning toward one color more than another. So let's break down this passage. I'm going to make a space here. I think I'll just use a basic main idea map. And I think I will go ahead and split it so we have room for our topic and our main idea. And definitely our topic will include that phrase, chromatic bias. And the main idea is that chromatic bias or color bias influences how we perceive, that's a big word too, color. Okay, and then they give us an example of this blue, I'm just going to call it the dress. And I remember this picture, it was all over Facebook, where you look at this picture, some people see a blue dress, some people see a white dress. So they're using that example of the Facebook dress as an example of how this process works. Now, if you don't have Facebook, you will probably not have seen this particular story. This is why I encourage you to read, even if it's on Facebook. That's better than not reading at all. Be careful what you read on Facebook, but if you read anything, you're building your reading comprehension. So this happened in 2015, just as a detail. And so what was the issue? We know the example was the Facebook dress. And you might be thinking, well, shouldn't that be the topic? Because the whole passage is talking about this dress. And we'll come back to that idea in just a minute. Some saw a blue dress with black lace, so blue and black. Others saw white and gold. I personally never saw the blue and black. I only perceived the white and gold. So that's sort of the issue as to what was happening. Some people, and there was a big argument about it, some people would just be adamant that that dress is blue and black. And I was seeing white and gold. I never saw blue and black. So why? That's the question that we're answering here. Why would my eyes see one thing and your eyes see something else? And the answer to that is our topic. It's chromatic bias. So let's explain what that means. We know that it has to do with seeing one color over another, but why? What is it that makes us see color? Well, some colors, let's say some light, some colors of light, bounces off an object. Okay, so if you look at something and you see white, Let's not use white. Let's say that you see red. Okay. That means that red is what your brain is perceiving that color to be. So let me show you an example. I don't want to make this worse, but let's say that there is a red apple. And let me just go ahead and pull up, if I can, a picture of an apple. So if you'll bear with me just a second, I'm going to say apple clip art. So I'm just Googling a picture of an apple, and this one will be just fine if I can get it to save for me. And I maybe can't, but we'll try. I really should be worrying about the copyrights on these, but I think I'll just not worry this time. Here we go. So let me cut this down. So here's a picture of an apple. Have you ever stopped to think about why this apple appears to be red? Why is this apple red? That's what we're talking about here. Now, some people may look at this apple and say that apple's not red, that apple is pink, or that apple is orange, because their eye is perceiving the color differently, just like this story is talking about the dress. Okay, so this tells us, let's go back to the passage. I need to stick to what they're telling me and help you learn to do this on your own. It says, our brains determine which color of light is bouncing off an object. Then they subtract that color to determine the real color of the object. Which color let's stop there. So as I look at this apple, I see red. I see a green leaf and a brown stem. What is happening scientifically that is making me see that? Well, when my eye looks at that image and the light bounces off, so I see, let's do it this way. My eye is looking at this image, and then it rebounds. It bounces off. It's reflected off of the apple. So I'm looking at the apple. Light is coming back this way. Blue light is being reflected. Yellow light is being reflected. Green light is being reflected. Indigo light is being reflected. Violet light is being reflected. Orange light is being reflected. Which color is not being reflected? Which color is being absorbed? All of these are being reflected. Red is being absorbed. So my brain says, oh, that apple is red because that's the color of light that is not bouncing back. That's what they're talking about with subtracting color. So red is absorbed. To my eye, the apple appears red. On this leaf, red is being reflected, but what's being absorbed? Green is being absorbed. And you might be thinking, this passage doesn't say anything at all about an apple. And that's true. I'm just using that as a way to explain this process and how all of this works. So on the dress, you have this dress here. Let me see if I can find the dress. I'm sorry if you hear that in the background. That is my blood sugar alert, that my sugar is dropping a little bit low, but I think I'll be okay for just a few more minutes, but I apologize for that noise that you're hearing. Here's the dress. Okay, let me just pull up this picture. This is the dress that everybody was discussing. Now, depending on how your eye perceives light, you will see this as probably blue or gold. And I will tell you which one I see. Let me just post it down here. Well, it's not going to do that. So let me go back and pull it up just on the internet. So here is the picture of, quote, the dress. This is the dress that we're referring to. Some people perceived it as blue with black lace. Some people perceive it as white with gold lace. Just depends on how your brain perceives it. It depends on what your brain perceives to be as the reflection. Now, in this picture, I see both. In the original picture, I only saw the white version. I never saw the blue. So, main idea. Which color dress we see depends on which color of light our brains determine is bouncing off the dress. So we need to go back to our main idea and add to that just a little bit. Chromatic bias influences how we perceive color. I'm not going to change it. I'm just going to add to it. Because different brains see different reflections. Okay, let's go on down to the bottom of this page and learn a little more about this subject. When we look at something, light enters our eyes through the lenses. Different wavelengths of light correspond to different colors. Then the light hits the retinas at the back of our eyes. The pigments in the light set off neural signals to the visual cortex. The visual cortex is the part of the brain that processes those signals. Then our brain recognizes what we see. Well, the first thing that pops into my mind as I read this is a timeline. Now, in this case, time starts here and it goes forward. It doesn't go both directions. So I'm going to use an end point and an arrow. The next thing that jumps out at me is the number of scientific words in this passage. I would call retina a scientific word, neural, cortex, visual, maybe even wavelengths. So let's take a minute and figure out what these words mean, because this is that science vocabulary. It is academic vocabulary. So let's start with wavelength. Now this one you can figure out if you know about compound words. A wavelength is the length of a single wave. And you say, okay, that doesn't make any more sense than it did before. That's a tough definition. Let me show you an example of that. We've all seen one of these. I would bet on it. Everybody recognizes the rainbow. But have you ever stopped to think about what makes a rainbow? Let's study this just a second. Rainbows are always in this order: red, orange, yellow, green, blue, indigo, violet. Always. It doesn't matter where you see the rainbow in nature, it will follow this pattern. And here's the reason. It comes down to wavelength. If you look at the red arc and compare that to the violet one, the outer one and the inner one, what do you notice about the red one? Its wavelength is longer. Red is the longest wave. The violet in the middle is the shortest wave. Green is in the middle. Green is right between the longest and the shortest, and it will always follow this pattern. So the length of one red wave is longer than the length of one yellow wave. Red is always the longest of the wavelengths. So that's what we're talking about with wavelength in this particular story. Retina. Now, if you need to look this up in a dictionary, go ahead and do that. But it tells us the light hits the retinas at the back of our eyes. So we can use context clues and definitions here. The retina is the back of your eye on the inside. I'm going to take it a step further and say the back of your eyeball. Neural. This is a tough one. You might have to look this one up. But if you know that N-E-U-R is the root for nerve, neural is relating to nerve. So when you say neural signals, you're talking about nerve signals, the nerves in your body. Visual relates to vision, which relates to the eye. And then cortex, this one you probably would need a dictionary. There's nothing really that tells me anything in this passage other than the visual cortex is the part of the brain. So cortex in this case is part of the brain. So there's our science vocabulary. And let's see what this sequence looks like. So the first thing that's happening, when we look at something, light enters our eyes through the lenses. So I'm going to say light enters the eye through lenses. Each of your eyes has a lens, and the light passes through. Okay, what's the next thing that happens? Now, I know that this sentence is there, but that's not something that occurs. That's just a fact of science. The next thing to occur, to happen, is this. That light hits the retinas at the backs of our eyes. So the light enters through the lens, it hits the retinas, and we've already said that the retinas are the backs of our eyeballs. Then what happens? The pigments in the light set off neural signals to the visual cortex. So there are particles, there are pigments, colors in the light. Cause, that's another word for set off. So we have a cause and effect happening here. And instead of neural, I'm going to say nerve signals. To go to the visual cortex, I'm just going to say brain. Because remember, I'm trying to understand this in everyday terms. So I'm translating it into terms that I can understand. Now, here's another one of those things that it's not happening. It's just a fact of science, that the visual cortex is the part of the brain that processes the signals. And then what's the next thing that happens? Once the brain processes those signals, our brain recognizes what we see. So let's review just what I've written down here on the timeline. We look at something. That really should have been the first step. And actually, let me go ahead and change that. You don't have to do this, but I should have caught that. So I'm going to move that on over. And I'm going to remove that so that I can add just a little bit of my line, and we'll make this become the beginning spot. So this all starts when we look at something. Maybe it's that apple or that dress we were talking about. Then light enters the eye through the lenses. It travels through the eye until it hits the retinas in the back of the eye. Pigments in the light cause nerve signals to go to the brain, and the brain recognizes what we see. So this is a very simplified version of what happens, and this will give us our topic. What is this describing to me? This line, what's it describing? How we see. The main idea, or a main idea that I could come up with here. Vision depends on light, the eye, and what else? The brain. Remember, that main idea should include everything that we're talking about. So we've learned some new vocabulary. We've learned 2 rules of science here in yellow, that different wavelengths of light correspond to different colors. We looked at the rainbow. We learned what the visual cortex is. And we learned how this process works. All in this little passage. It's all in there. That's one reason science passages can be very difficult. We also reviewed our context clues. We reviewed sequence, topic, and main idea. So this is a much more difficult passage than some we've read. So let's see about this question. Now, I know they already tell us the answer, but let's look at it before we look at the answer. What happens immediately after light hits our retinas? So here is the point where light hits our retinas. What happens immediately after that? Light enters our eyes through the lenses. No, that was over here. That was before the retina. The wavelength of light corresponds to a certain color. That's true all the time. Pigments in the light set off nerve signals that go to the visual cortex. There we go. That is what I have written up there in my section. Or our brains recognize what we're looking at. Eventually, yes, but that was not immediately after the stop at the retinas. So this is going to be answer C. Okay, I'm going to stop this video, and I'll stop that cell phone from ringing like that. And then in the next video, we'll look at page 35, which is a much longer passage. So I'll see you soon. Bye-bye.